we are going to talk about expressions, equations, and exponential growth and decay. So let's go over some things that we have learned in the past. Uh, you might remember that an algebraic term is a group of letters and numbers linked by only multiplication and division. So these are examples of algebraic terms. Variables are the letters in the algebraic terms, that those unknown values. Coefficients are the preceding the variable or variables, that number. Now remember, if you just see an x, the coefficient is technically a 1. If you see a negative something, a negative x, the coefficient is -1. So sometimes there's some there that you don't really see. Like terms have identical combinations of letters. Those variable factors and their powers will be identical. So if we look at these lists of terms here, um, if they have more than one variable, every single one of the variables and the powers on those variables have to match. So 5a cubed b and 2a cubed b are like terms. 3 radical 3ab and -3ab are like terms. So you have to be mindful of the variables and their powers. They have to match to can be considered like terms. So let's take a look at this. And if we're asked to simplify by combining like terms. So what I'm going to do is I'm going to go down the list here. We've got 5a cubed bc squared. And we see another one of that exact combination, a cube on the A, a square on the C, and then the B just doesn't have a power, or that is considered a first power on these two terms right here. So when you're combining like terms, you're just going to keep the variable piece of it, and you're going to add or subtract or combine the coefficient portion. So this is really, I've got 5 of these things minus 2 of these things. I have 3 of those a cubed bc squared. Okay, but now let's see, are there others that are like terms? Well, we have an ABC here, we have an ABC here. So those are like terms. So if we have -7abc minus 3abc, we really are thinking, what is -7 minus 3? Well, that would be -10abc. And then the only term that we haven't considered is this one here. There are no other terms that have the same exact variable pattern there. So we're just going to include that on our list, but we don't have anything to combine it with or to change it. So that would be your final answer. We can't combine anything further because there are no other terms that are like terms. Now, if we have something that requires that we use order of operations, in this case, we have these parentheses here, that requires that we use the distributive property because these are unlike terms. We can't combine them. So the only way that we can deal with this 2 here is to use the distributive property. So what are we going to do? Well, we're going to take the 2 and we're going to multiply it by both terms that we see there. So we get 4x plus 6y plus 14x. Now that we have that multiplication done, because if you remember our please excuse my dear Aunt Sally, we have to have all multiplications done before we try to add or subtract anything. So now we just have to think about, are there any like terms that we can actually add or subtract? Well, these two are like terms. 4x plus 14x is a total of 18x's, plus that 6y, which is an unlike term. So you just leave it alone until we know the values of x and y. We can't go any further. So that would be your final answer. Now, this one it is very similar to the ones that we saw earlier. We do have a parenthesis there. We do have to use the distributive property again, this time with the 5. 5 times 2x is 10x. 5 times y, we're just going to write as 5y. Again, our only like terms are these two. So 10x minus 4x is a total of 6x's plus 5y, and you're done. So, where the parenthesis sits, uh, is going to impact that final outcome. And that's as far as you can go. Here's another one. This time, be careful. This -2 is in front of the parenthesis. So the most efficient way to proceed is to multiply each of these terms by -2. So we would get 8y minus 8y plus, because a negative times a negative is a positive. And so -2 times -3 is +6, and then the x is just there. Now this time our like terms are these two that we see here. They are exact opposite. You can think of that as 0 y's, but they're 0 times anything is still 0. So those two cancel each other out perfectly, and our final answer would be 6x. Got it some more. Same thing, just a little more complicated than the last. The 6th is in front of these parentheses, so we're going to distribute that. We're going to leave these two pieces alone, and then we'll see if we have any like terms. Now, if I multiply the 6 by the 5x, I have 30x. 6 times -2y is -12y. And you might notice here that these are like terms. Those can be combined, and these are like terms. So let's go ahead and do that. So 30x and 3x is a total of 33x. -12y plus 3y is -9y. Remember, if they're opposite signs, we're going to subtract and keep the sign of the larger value. This one is larger than that one. The absolute value of it is. So subtract, get 9, keep that sign on your 9. So it'd be -9. That's as far as we can go with that one. Because we don't know what x or y is, you leave it alone. And that is your simplified version. Now we have some equations that also have some distributive properties in them. We need to isolate that x. There are two ways to do this particular one. There's many ways to do equations. There's not one exact way that's perfect. I'm going to show you both ways. And then you can decide how you want to proceed. I see here that we have this 2. 2 implies multiplication. Let's go ahead and use the distributive property. So we're going to get 6x minus 14 equals 12. Now our goal here is to isolate the x term on one side of the equation and the non-x terms, those numerical pieces, on the other side. So let's add 14 to both sides. So we get that 6x equals 26. Now 6x means the multiplication of 6 and x is equal to 26. So to isolate the x even further, once you have that term isolated, go ahead and if you're multiplying by something, you're going to divide. If you're dividing by something, you're going to multiply. So we're going to just use the opposite operation. So divide everything through by 6. Now, 26 is not perfectly divisible by 6. So that's kind of your answer. But any fractional answer that you want to have simplified as much as possible. Both of these numbers are divisible by 2. So I would suggest dividing by 2 and getting an answer of 13/3. Now, if they say that improper fractions are okay as long as they're simplified, that's perfectly fine. Mixed numbers are also an option depending on how they want your final answer. 3 goes into 13 4 times because 4 times 3 is 12 with 1 left over. So that's how you would write the mixed number. Now I want to show you an alternative way to do this problem. So let me copy this and put it over here. And I want to show you another way that we could have proceeded. Since this entire side is multiplied by 2, we can undo that because I notice that the other side is divisible by 2. So if we divide both sides by 2 right off the bat, that's going to go away. We are going to be left with the quantity of 3x minus 7 equals 6. And if we proceed through it, you're going to see we're going to get the same exact answer. We would add 7 to both sides. We would get 3x equals 13. And then we would divide by 3. And you'll see it leads us right to the same place so that we get x is 13 over 3, or 4 1/3. So as you can see, and there's probably even other ways you could do this equation. There's no one perfect right way to get to the same answer. But I wanted to show you, some alternatives you have. You have a lot more power with an equation because of the fact that, it's an equation. So as long as we keep it balanced, do the same thing to both sides, it's not going to hurt anything. And we can proceed, and you might do it slightly different than I do it, or slightly different than your friend that might be sitting there helping you, but you can still get the same answer. Okay, let's do another one. Now this one, you'll notice that this quantity is not isolated. So you can't just divide this by 2. You would have to divide every single thing by 2. So that's not a good strategy for this one. Each equation has kind of a unique strategy that you want to take as you're going through the process. So what I would say here is, I would say let's treat each side as if it were an expression that we can simplify as much as possible. Okay, so that's 15. You can't do anything here, but we have lots of things we can do here. So the first thing I'm going to do, like some of the expressions we saw earlier, I am going to distribute. I'm going to get 4x plus 6x plus 14 equals 15. And I'm going to take that side and I am going to simplify it as much as possible. You might notice we have some like terms. 4x plus 6x can be combined to be 10x. Now, once you get to the point where both sides are simplified as far as you possibly can go, then you are ready to start moving things around. Okay, so this time we want the x term on one side, the numerical terms to be on the other side. So we have to subtract off 14 from both sides. So we get that 10x is equal to 1. And then 10 times x is equal to 1. So to solve for x, divide both sides by 10. We get that x is the fraction 1/10. And so, that's as far as you can go. That fraction is simplified as far as you can go. Sometimes the decimal is helpful, sometimes it isn't. If you wanted the decimal value, you can just put top divided by the bottom into your calculator, 1 over 10, or 1 divided by 10, will get you what you want to go. Okay, so there's that equation. Let's do another one that has some similar ideas to it. So we saw a very similar expression. It might have been the same one, but we saw a very similar expression earlier. We're going to attach the -2, and we are going to distribute that or multiply that by both pieces inside. So we're going to get 2x minus 6x plus 18. Make sure you use that -2 for both pieces. Make that look a little nicer. Equals x minus 15. Now the right side, even like this equation we saw earlier, is simplified as far as it can go. You can't combine those, but our left side still has some ways to go until it's simplified. 2x minus 6x is negative 4x. And once we get to the point where both sides are as simplified as possible, you want to start moving things around. So I want the x's to be on one side, and I want the numerical pieces, uh, those plain numbers, to be on the other side. Okay, so how do we do that? Well, it doesn't really matter which side you go to at this point. You can put the x's on the left or x's on the right. For an equation, you decide. Negatives can cause issues with some people. So if we add 4x to both sides, if I could write 4x, let me see. There we go. If we add 4x to both sides, our x's that are on the right will be positive, and that's a helpful thing sometimes. And then I am going to need to then, if I want my x's on the right, move my numerical piece, this 15, this negative 15 to the left by adding 15. And you can do it in two distinct steps, but I figure I know where I'm moving to. I can just do it as long as I do it to both sides. And what do I get? Well, on the left side, these are going to cancel. I'm only left with those numerical pieces. That's a total of 33. On the right side, my numerical piece moved, so it canceled over to the left. X plus 4x is 5x. And then I have to get rid of that coefficient on the x. I divide by 5. I get x is 33 over 5. Now, that is a perfect improper fraction that's reduced as much as possible. If they want a mixed number for our answer, that's okay too. 5 goes into 33 6 times with 3 remaining. So remember that 3 over 5 is what is remaining, 3 out of 5. Okay, so that is an equation that is a multi-step, lots of different things we have to do. Now, let's talk about exponential growth. During COVID, we saw those charts they were showing the news where the cases of COVID were growing exponentially. So if we talk about an infected person spreads a virus to 2 other people per week, that population is growing over time. We have some bacteria in a petri dish. Every day, the bacteria triples. That's an exponential growth. So the formula we're going to use, the most simple type of exponential growth formula, is that the total population, so you want to think of this as your total, and some texts will call that an A, is P, which is your starting population. 1 plus R to the T. R is your rate of growth. If it's growing, it's going to be positive. If it's decaying, you'll see 1 minus the rate will be a negative. Excuse me. And then the time is your T. So by knowing what the things stand for in your equation, you are able to use that formula just like we use like that Celsius to Fahrenheit or vice versa, those formulas, same idea. Okay. So you remember that this is your total population at any given time. This is your rate of growth. This is your starting population. So if 4 people started being sick and then they started giving it to people or whatever, if that would be your starting population. Okay. So let's write the formula down. I'm just going to put it up here. Okay. And it says a population grows by 45% every hour. The initial population is 200. So all we're going to do is going to kind of set up an equation that stands for that information. Okay. So we're just going to practice doing that. So the initial population is 200. It is a growth rate. Our time is hours. And our rate is a 45% growth. So it's going to be a positive 45%, which most of the time we're going to use that decimal equivalent. So move that decimal 2 places to the left or divide by 100. It's 0.45. Okay, so let's set up an equation for this particular situation. The final population at any time for this situation is 200 times 1 plus 0.45 to a power of t. So the formula we would get is 200 times 1.45 to a power of t. So you'll see in that parenthesis, the 1 is your like 100% what it starts with. Your 45% is what it's growing by. So 1 plus 0.45 in the parentheses. And then your t is every hour. So if you wanted to know what would the population be after 3, or how many, yeah, what is the population after 3 hours? What is the population after 7 hours? You would just be able to use this formula. So as you can see here, the P is 200, the R is 0.45. That's the formula that we're talking about. So let me write down or copy this formula, and let me show you how we can use it. Okay, so there's the formula. So after 1 hour, it would be 200 times 1.45 to a power of 1. Now you just want to add that or enter that into a calculator. If you were doing it slightly by hand, we would have to use order of operations. 1.45 to the first is 1.45. So that'd be 200 times 1.45. So after 1 hour, let me tell you what that is. 200 times 1.45 is 290. So they didn't say if it was bacteria, if it was people, it was whatever. But we looked at the population initially, it was 200. After an hour, it's up to 290. What about 2 hours? So that would be 200 times 1.45 to the second. So we would have to do the 1.45 to the second power or squared first. So it'd be 200 times 2.1025. And it should be more than 290 because it's growing again that next hour. So 200 times 2.1025 is 420.5. Now, for bacteria, they might leave it that decimal. If these were people, you wouldn't say half a person, and they would either specify, some texts will round that up to 421. Some will say, well, that half a person isn't a full person yet. Just truncate it and just leave it 420 for this particular problem. So just read the instructions. How do they want you to round? Nearest whole number is pretty common. So you'll see either 421 or 420, depending on the application. Okay. We're going to use it one more time for 5 hours. So we should have more than 421 people. So the population is 200 times 1.45 to the fifth. We should see it grow again. 1.45 to the fifth is a very large decimal. So what I would do is I would leave that calculation into the calculator, because my calculator, it's like 6.409734, just leave that calculation right there sitting in your calculator, 1.45 to the fifth, and then hit times 200. And so we get 1,281.9, which they might leave 1281, or they might round up to 1282. So if they say round to the nearest whole number, it would be 1282. If they said, just keep that front number It would be 1281. So again, you'll have to look at what the instructions say. And then it says, when will there be approximately 53,000 in population? So we want to know, when will the population hit 53,000? So what hour? So it'd be 1.45 to what hour? Well, there's a mixture of ways to solve that. First, take 53,000 and divide it by 200, because we can divide both sides by 200 to make our life a little easier. So we need to know 265 is equal to 1.45 to what power of t? Now there's a way to do that into a calculator. Um, there's a button that where I'm going to show you how to use that. Um, we can't just, unfortunately, just divide off the 1.45. It doesn't work like that. It's a base. So we can't do that. You can start estimating, if you do 1.45 to the, remember, to the fifth power gave us 1282. So, try to the 10th power. Is that too much? Um, it's not too much. How about 20? 20 is more than we want. So it's somewhere between 10 and 20, and you could keep messing around until you find something closer. I'm just kind of playing here. 15, 1.45 to the 15th power is really super close. Okay, it's 263. But how can we find it exactly? Well, almost every calculator, scientific calculator, basic scientific calculator, has a button on it that says either log or natural log. It doesn't matter which, both will work. Okay. All you're going to do is you're going to take, we'll just put log for now, of 265 equals the log of 1.45 to a power of t. And all you have to do now, it's just a rule for logarithms that the t can drop down in front. I'm going to kind of make a formula for you in a second here. And we get that the log of 265 equals t times the log of 1.45. And so that t is the log of 265 divided by the log of 1.45. Okay. So you would just hit in your calculator. It can be the ln button, that's a natural log, or the log button, it doesn't matter. So the log of 265 divided by the log of 1.45. My gross handwriting, is what that says, is 15.01. So it's about 15 hours. Okay. Now let's go back to this step, and I want to write a formula. Let's say that we have a number equals some base to some power. And I'm going to put a P up there because it might not be T, but in these ones it's T. But okay, so if you want to solve that for P, okay, so in this case that's our T. Here's the formula you can use for now on, okay? We know that the log of the number divided by the log of the base is equal to the power. So that's a nice little formula that you can use to solve for when your unknown is your power. You have to use either the log button, or it also works for the ln button on your calculator. Um, so I don't know how many there'll be like that, but I did want to show you that formula. Okay. Now here we're looking at a decay of some sort. The half-life is the time it takes for a population to reduce by half of what exists. Medications. So when you ingest a medication, it starts breaking down in your body and it has a half-life. Now, some have half-lives that are very, very quick. It starts breaking down maybe in hours. Some might be days. Some might be minutes. When you ingest caffeine, caffeine has a half-life. So it takes 5 to 6 hours for a healthy adult to eliminate half of the caffeine that they've consumed. Just a little note there. So if you look at this, the formula for half-life is the amount is the initial dose times 1/2 to a power of the time elapsed over whatever the half-life time is for the medication. So I know it's not medication, but let's think about that caffeine um, uh, analogy for a minute. Let's say we took um, 50 milligrams of caffeine, and we know the half-life is 5 hours. We'll go with 5. And so let's say that 2 hours have passed, and 2 hours have passed, and the half-life time is 5 hours. That's what we would put into our calculator. Now, how do you put that into your calculator correctly? Well, you're going to get 50 times, you're going to put 1/2, you're going to hit that caret button, and in parentheses, you have to hit 2 divided by 5 or the fraction 2/5. So after 2 hours, you ingest 50 milligrams of caffeine. And let me tell you how much caffeine is left after 2 hours in your body. After 2 hours, there is 37.9 milligrams left in your body of caffeine. So just a little, just some information there for you. So let's take a look at this one. Now, let me copy the formula so we have it. Wait a second. Okay, there we go. So now we got the formula here. It says a medication has a half-life of 3 hours. If the initial dose is 350 milligrams, how much will be in the patient's system after 6 hours? Anytime you do a word problem where a formula is associated with it, my suggestion is to write down what is the stuff that we know. Okay, so here's what I think about. The half-life, so that's T with that 1/2 subscript, is 3 hours. The T is that top of the fraction is 6 hours. The initial dose, I'll call it ID, is 350 milligrams. The question is how much is the amount? How much is in the patient's system? Okay, so we're going to go A equals 350 times 1/2 to a power of. Now, on the top of the fraction is how much time has elapsed, 6 hours. The bottom of the fraction is the half-life time, 3. Now, in our case, 6 divided by 3 is exactly 2. So if that reduces down, go ahead and do that. And you're going to do 1/2 to the second power, which is 0.25, 1/4. And then 300 times 0.25 is 75 milligrams. So the patient will have 75 milligrams left in their body after 6 hours. So that's a little bit about some medication dosing. As long as you know the half-life of it, uh, you can use that formula. So there you go. I hope that helps you understand that a little better. You have a wonderful day.